In this video, we'll be reviewing the dot product or scalar product of two vectors. The dot product is a way of multiplying parallel components of two vectors, and the result is just a number, not a vector, so that's why it's called the scalar product, because it gives a scalar. One way to express the dot product between two vectors a and b is the magnitude of a times the magnitude of b times cosine of the angle between them. And remember, this angle between a and b assumes that you're drawing both vectors from the same point and then finding the angle between the two vectors. Another way to express the dot product is using the vector components, and I'll mention briefly how to get this result. We begin by writing each vector in Cartesian form with components and unit vectors. We can now distribute term by term, but the definition of the dot product will make this much simpler. All of our unit vectors are perpendicular to each other, meaning that there is not parallel pieces to multiply, and the result is 0. So by definition, the dot product between any two vectors that are perpendicular is always 0. This means only the terms with like components will survive. And the magnitudes of the unit vectors are just 1, so they sort of disappear when multiplying by 1. Then we're left with the product of like components all added together. Both of these ways of getting the dot product are equivalent, but you may want to use the first one when you know the magnitude or size of your vectors and the direction, or the relative direction between them, or the angle, and use the second one if you have the components of the vectors rather than their magnitude and direction. But of course, you can find the magnitude if you have the components. Now I'll take both of these and combine them to get another use for the dot product. Since the dot product depends on the angle between the vectors, because the angle will determine how parallel they are, we can use the dot product to find this angle. First, we solve our first expression for the angle, getting inverse cosine of the dot product over the product of the magnitudes. This is just using some algebra. Now, in place of the dot product in the numerator, we can plug in our second expression for the dot product in terms of the components. So as long as you know the components of your two vectors, you can use this to find the angle between the vectors. If you don't know the magnitudes offhand, that's fine, because you can just use the Pythagorean theorem to get each one and then plug in to find your angle. You probably saw the dot product after you were comfortable with vectors and using sine and cosine to find vector components. I want to quickly show you that the dot product was there all along. If we take this vector a and want to find ax and ay, another way to state this is to say we want to know the amount of vector a that is parallel to I hat, or the x-axis, and the amount of vector a parallel to j hat, or the y-axis. If ax is the amount of a parallel to I hat, then we can write ax as the dot product of a and I hat. This would give us the magnitude of a times the magnitude of I hat, which is just 1, times cosine of the angle between them, which I'll call theta 1. This matches what we would normally get when finding ax the way we're used to. If we do the same for ay, we should take the dot product of a and j hat, giving us the magnitude of a times the magnitude of j hat, again just 1, times cosine of the angle between them, which in this case I've labeled as theta 2. The dot product uses the angle between the two vectors, so we cannot just use the cosine of theta 1 again. But when we normally decompose vectors, we get one component using cosine and the other using sine. But in that case, we're using the same angle. We can replace theta 2 with 90 minus theta 1, as you can see from the picture. And since sine is just cosine shifted by 90 degrees, or pi over 2, however you want to write it, we can write ay as a sine theta 1. So why do we do this? This shows you another powerful use for the dot product. We often use unit vectors I, j, and k hat corresponding to directions along the x, y, and z axes, but we could have unit vectors in any direction. We can use the dot product between any vector and a unit vector in any direction to find out how much of our vector is pointing in that direction. This is often called a projection, or projecting a vector along some direction, and it's just a simple use of the dot product. I like to think of it as finding the shadow formed by a vector in some direction. In the same way, ax looks like the shadow of vector a being cast onto the x-axis in our picture. I'll also have a video on unit vectors that may help you when you're using the dot product in this way. So to quickly summarize, the dot product or scalar product multiplies parallel components of two vectors and always gives you back a number. It does not give you back another vector. It can be used to find the angle between two vectors, to find the projection or component of a vector along any direction, but commonly x, y, or z. And finally, you can determine if two vectors are perpendicular by evaluating the dot product between the two vectors and seeing if you get 0. So that's it for this one. I'll see you in the next video.